In this R tutorial, we'll learn how to visualize whether there's evidence of adverse or disparate impact using bar charts in R. So to get started, we have RStudio open here. You can see the console is open. Let's get a new file, R script open here so we can access an R script editor so we can save our work in the script as we go along. I'm going to paste in the title here just to remind us again what the purpose of this R tutorial is. It is to visualize evidence of disparate or adverse impact using bar charts. Now, typically what would be done first is that some type of adverse or disparate impact test would be run, such as the 4/5 rule would be evaluated, or some type of statistical test like the chi-square test of independence with or without the Yates continuity correction, or maybe the Fisher exact test, or the z-impact ratio, or the z-difference test. And so assuming that you have some type of finding from one of those tests or multiple of those tests, then you might proceed forward with actually visualizing the results of your findings and visualizing evidence of disparate or adverse impact or the lack thereof. So let's get started here by first making sure that we set our working directory. And I'm going to do it with the setWD function from base R. As a sole parenthetical argument, I'm going to enter a path extension here, which is my H drive R workshop folder here. I happen to know this one off the top of my head. This is where the data file I'm going to be working with today comes from. Most likely you'll need to set your working directory to a different drive and a different folder, a different pathway on your computer. And this is going to be wherever you've saved your data file or wherever you're going to try to access your data file. So I'm going to run this. Now remember, alternatively, you could go to Session, Set Working Directory, and Choose Directory to use the drop-down menu approach, and you can find the folder where you have already saved or you plan to save the data for this particular exercise or tutorial. Now this is also going to be, if you export anything, such as today when we have our plots and we can export, anything that you export will by default go to your working directory unless you tell it otherwise. Okay, so the next thing that we need to do is read in the data that I mentioned is already saved in my H drive R workshop folder. And hopefully you've downloaded this and it's available in a folder and you've set this working directory successfully by this point. So let's read in the data. And I'm going to use the reader package and specifically the read_CSV function today. And if you need to and you want to use that reader package and you haven't already installed it, you would run this install.packages function here. And as a sole parenthetical argument within quotation marks, you would enter the exact name of the package, which is all lowercase READR. And I have recently installed this package and it's up to date for me. So I'm not going to run this. So I'll put a hashtag in front of it to annotate it out so R won't run it as part of this script. However, if you do need to run this, by all means, please do it at this point. And you'll get an error if you try to access the package in this step where we use the library function to actually access the package. And so you'll know if you don't have this package installed, or maybe you'll get an error or a warning message indicating that it's a bit out of date. Okay, so I'm going to run the library function with the reader package here as a sole argument. Click run. See the stop sign going, blue text down here. Everything looks pretty good so far. I'm going to read in the data and I'm going to name this data frame object I'm going to read in and assign the, this is going to be the data frame object here that I'm calling df, lowercase d, lowercase f. And this is the object that I'm going to assign the data to. And this ends up being a data frame object. And so I'm using the left-handed arrow operator here in R, and this is how we can do variable assignment there. All right, so to the right of the left-handed arrow, I'm going to specify the read function that I'm using here, which is read_CSV from this reader package. Now the name of the data file here, I'm going to enter it in quotation marks, and I happen to know that it's called disparate impact.csv. Make sure you include the .csv file extension here if you're using a function that is specifically geared towards reading in .csv files, which stands for comma separated values files. And note that R is case and space sensitive, so you need to make sure that the file name has the proper punctuation and has the proper capitalization, lowercase versus undercase, and so forth, uppercase and so forth. So you'll notice here that disparate has a capital D, impact has a capital I, there's no space between them, and then again, make sure you have the .csv extension there. So I'm going to click run that, and you should see it pop up in your global environment, df. This is the data frame object that I arbitrarily called df. You could call it anything you want that begins with a letter. And so just make sure that it goes to the left-hand side of that variable assignment or the left-handed arrow operator there. Now, if you don't want to use a specific function like the read_CSV function that comes from a package that you need to install, you can use one that comes with base R, and I'll just copy this real quick to show you how you would do that. Copy that line, paste it. The only thing that you'll change here is the underscore to a period, and so it's read.csv now. This read.csv function comes from base R, meaning you don't need a special package installed to access it. It works functionally the same, except there are some advantages when you're working with more data, larger amounts of data, and so forth, to use the read_CSV function. And this technically reads in data as a tibble, which is a mixture of a table and a data frame, essentially, where a data frame is a specific type of table. And whereas a read.csv is going to read in the data as a traditional data frame. All right, I'm going to annotate this line out here because I already read in the data successfully with the read_CSV function, but if you wanted to use this one, you would just run this line right here. All right, so now we are ready to, well, let's start by actually creating a contingency table. We need to organize our data, and I'll show you the data in just a second so we can make sense of it and understand the context. Now, sometimes you'll hear a contingency table referred to as a cross tabulation. It's the same thing. So let's click on our global environment here on the object we call df, that is our data frame object here. You'll see that there's 274 observations and 3 variables. 274 observations corresponds to 274 unique applicants who are applying for a job and going through a selection process in this particular organization. And so if you were to scroll through the data here, you'd see we have 274 people. There's a unique identifier variable or applicant identifier variable that is capital I, capital D. We're not going to use that today, but that is just to give us an idea that each one of these rows represents a unique human being and a unique applicant to this selection process. Now, the 2 variables of interest here are cognitive_test and gender. Cognitive_test, this is our cognitive ability test, let's assume. So these applicants have all participated in this cognitive ability test, and they either get a pass score or they get a fail score. So this is a dichotomous categorical nominal variable if we're talking about the measurement scale here. Now with gender, it is also dichotomous under this particular example here. And so gender identity here, let's assume that it was self-reported by the applicants themselves. And so here we have man. And if you scroll down a little bit further, you'll see that we also have woman here. Okay, so there's 2 levels to this gender variable here, man and woman. So also categorical, also nominal. So we have 2 categorical variables here. Okay, and so what we're going to end up doing with this contingency table is creating a counts or frequency table. And you'll see what this looks like in just a second. And so we're going to be using the xtabs or the crosstabs function from base R. It's just xtabs, all one word, and all lowercase. And after xtabs, enter, create your parentheses. And as your first argument, start your argument with a tilde. Okay. And the next thing that you're going to do is you're going to specify the variables in your contingency table, your cross tabulation. And first, let's enter the protected class variable here, which is gender. Okay, followed by the plus sign operator, and then followed by the selection procedure, employment practice that we wish to evaluate whether there's evidence of disparate or adverse impact. And so that happens to be called the cognitive test here. Okay, and if you're wondering where I got these exact names, look at the data frame here. Make sure that you've spelled it correctly and they use the underscore where the underscore is supposed to go with the cognitive test, and make sure the C is capitalized, the T is capitalized, and make sure the G in gender is capitalized as well. Now, if you want to copy and paste those specific variable names in, you could go down to your console here and just type in the names function from base R and type in df for the data frame to see what are the names of the variables in that data frame. Hit return or enter, and you'll see you could just double click, copy, and paste these in here. Okay, that's a way to make sure that there's no transcription errors. All right, so this right here before the comma is our first argument. As I mentioned, we've just specified the contingency table that we'd like to set up here. Now, the second argument is going to be the name of our data frame. And so we'll do data equals and the name of the data frame object, which is df here. This is what we named it over here when we read in our data. And this is the data frame object where these two variables here, gender and cognitive test, live. And so now let's run this, see how this works out. And so now you'll see we have a 2x2 contingency table here, a 2x2 cross tabulation, if you will. And you'll notice that we have gender corresponds to rows here because we put gender as the first variable here before the plus sign operator. That means that man and woman are going to represent the rows. And then because cognitive tests came after the plus sign operator, that's going to be our columns here. Okay, fail and pass. And so each of these numerals here, these numbers represented, are raw frequencies or counts. So for example, 70 of the men who took this cognitive ability test passed it, 42 of the women who took it passed it, and so forth and so on. But let's go a step further, and to the left of the crosstabs, the xtabs function, let's do the left-handed arrow operator so we can read and assign these data over to an object that we can subsequently reference. And let's call this object arbitrarily observed. The reason I'm calling it that is these are the observed frequencies. And this would make a little bit more sense if you had previously done a chi-square test of independence with these data, because when you do a chi-square test of independence, you're talking about the observed and the expected values, okay? So here we have the observed. This is an object. Again, you could call this whatever you want. I'm calling it observed all lowercase. Let's run this line. And now you see we have a new object over here, and this is our observed object. And if we want to verify that it correctly, that the contingency table was correctly assigned to this new object we created, we can just highlight that by double clicking it and click run, and you see there we get verification. It's the same contingency table that we saw above. We ran the crosstabs function by itself. All right, the next thing that we are going to do is we're going to actually create a new object where we are going to convert the contingency table to proportions table. And we're going to do so by gender here. And so what I mean by that is let's create proportions so that each row here, which happens, gender is the rows here, man and woman, that the proportions will add up to 1. So the row marginal for man, for example, will be 1.0, which is, if you add two proportions together, that would mean that they're adding up to 100%, essentially. Okay? And so that's what we're going to specify here. And how do we do that? We are going to use the proportions function from base R, very appropriately named there. And the first argument in the proportions function is the name of our table here, this table object we created, which is observed. So let's just copy and paste that in to make sure there's no transcription errors. Add a comma so that we can add a second argument here. And the second argument was where we specify how do we want these proportions calculated, because we could do them by columns, we could do them over the entire table, or in our case, we want to do them by rows or gender here. So this is where we specify the variable within each level, the proportions will add to 1.0 or 100%. And so in quotation marks here, type in the exact name of the variable here for our rows, which is gender, okay? If you had set up your table the other way around where you did cognitive ability plus gender, then you would still just put gender here. This function is smart enough to know that instead of rows, it'd be grabbing columns. It's just looking for the variable that it will add up within each one of those levels, those proportions to be equal to 1.0. All right, so let's see if this works here. Highlight that, click run, or you could just put your cursor next to it and click run. All right, let's verify this, and now you can see what I was talking about there. All right, so you'll see if we look across the man row here, so men who took the cognitive ability test, we see that about 43.8% passed and about 56.3% failed. If you add those two values together, you get 1.0 or 100% there. The same goes for women here. And so what you'll see built in here is this is actually our selection ratio or selection rate or pass rate for men is 43.8% here or 0.438. We're talking about proportions. And for women, it's 0.368 or 36.8%. Okay, so we've already computed our selection ratios here. And so that's why we specified that we wanted the proportions calculated by levels of gender there, okay, or categories of gender. All right, so the next thing that we're going to do is we are going to use our friend the left-handed arrow operator once more and put it to the left of the proportions function here. And let's create a new object name that we can assign this proportions table to. And I'm just going to call it prop_observed, because to me that makes sense. Proportions of the observed table. Okay, you could call it whatever you wanted, but this is what I think makes most sense here. You can make it shorter too if you want it. Let's click run there. Looks like it ran successfully. Let's double click this and highlight just the name, prop_observed, click run. Okay, looks like everything was assigned properly. All right, so now we are ready to pull just the selection rates or pass rates, okay? Because remember, this column here under pass has our selection rates, okay? And our selection ratio is just simply the number of people. So in this case, the number of people from a particular category, so in this case men, 70, who passed this particular employment test or selection test. So it's 70 here for passed over the total number divided by the total number, that is, of people who took this test from that group or that subgroup. Okay, and so for men it would be 70 divided by 160, where 90 plus 70 is 160. That's giving us our pass rate or selection ratio. All of those terms are more or less synonymous in this context. All right, so what we want to do is just grab these two values here, okay, 0.4375 and 0.3684, and pull them away so that we can use them and reference them in a bar chart function subsequently. So how are we going to do that? So let's create a vector of selection ratios, which we'll abbreviate with capital S, capital R, lowercase s, okay? And let's just call the name of this vector object we're going to create SRS with a lowercase s at the end. So capital S, capital R, lowercase s, okay? So this is a little bit of a test of the case sensitivity there. And so this is sometimes different people have different preferences in terms of what they like to name things, in terms of if they even use uppercase or they only use lowercase, or they use a mixture, or they use a kind of a camel's hump approach where they start everything lowercase and then they might, for example, do an uppercase O after an underscore. I like to do it this way, so I'm just going to do capital S, capital R. This is an acronym for selection ratios, and then lowercase s to make it plural. And so to the right of this object name that I've arbitrarily given here, let's do the left-handed arrow operator so that we can assign a vector to this object so we can subsequently reference it. All right, so what we're going to do is let's double click here and let's copy the exact name of this proportions table we just created, because again, this contains our selection ratios in this pass column here. And we're going to use matrix notation here by entering brackets. Okay, so not braces, not parentheses, but brackets. And the way that we're going to grab just the second row here, which is the pass, or the second column rather, that has our pass rates or selection ratios, is we are going to do comma 2, okay? And the way matrix notation, if you're not familiar with it, works is that the value you put before a comma, if any, references the row, and the value you put after the comma references the column. So this is giving dimensions here. And if you were to put a value before, I'll just put this here for an example, if you put 1, 2, we would be saying we want row 1 and column 2 here. So row 1, column 2. So column 1, column 2, row 1, row 2. So row 1, column 2 would be the pass rate or the selection ratio just for men, okay? But we want both selection ratios for men and women here. So we will just leave it blank before the comma so that we grab all the values in that comma or in that column in the second column specifically that has our pass rate, selection ratios. All right, so we can verify this by just running this chunk right here. And you'll see man selection rate here, woman selection rate, this checks out. This is our vector here, okay? Now if we highlight this and run the whole thing, you'll see that now we have another new object here, and this is our selection ratios object, capital S, capital R, lowercase s, all one word. All right, so now we are ready to create our bar chart. And what we're going to be doing is plotting the selection ratios. So you'll see two bars. One bar plots the selection ratio for men, 1 for the selection ratio for women. Okay? And so the way that we'll do this in this tutorial is we'll just use the stock bar plot function that comes with base R. I should mention that there's other types of packages you can download that do some really sophisticated and give you a lot of flexibility and customization options when it comes to data visualizations, such as ggplot2, plotly, dash, and Google Viz, and so forth. All right, so let's use the bar plot function from base R. It is bar plot, all lowercase, B-A-R-P-L-O-T. Base R, you don't need a specific package to access this function. Comes standard when you install base R on your computer or access it through the cloud. So let's start off with just a very simple implementation of this bar chart. And instead of typing that in directly, I could just copy and paste the exact name of that vector of selection ratios. So capital S, capital R, lowercase s in this case. And if we just run that by itself, you'll see that we get a very basic bar plot here. So here's our y-axis that contains, in this case, these are the proportions, which are our selection rates or ratios here. And then here we have a bar for men, a bar for women. And so we know that the selection ratio for men is about 0.44. And you can see the axis actually ends before that. But you can see where that would be 0.44 in terms of its height. And for women, it's 0.37 or so. And here you can see that it's about 0.37 or so. So you can see this is a way to compare. Now let's kick this up a notch here by adding some sophistication and refinement to this table. So I'm copying and pasting that script. I'm going to start adding some additional arguments here. So adding a comma here, I'm going to separate these arguments also by lines here so that it's hopefully a little bit clearer to read. Let's create some x-axis labels and some y-axis labels. So I want to make this more clear what we're talking about here. So for the x-axis, I'm going to add a label that is just gender, so which would correspond to man and woman here, so the gender identity is there. And then for the y-axis, I want to name this selection ratio and also indicate that this, for people that might be familiar with this term as a pass rate, put that in parentheses. So how do we do that? Well, with the bar plot function, there's some built-in arguments like xlab, which stands for x-axis label, okay? And if we do xlab equals and in quotation marks, we can type whatever we want for the x-axis label. And I'm going to just type in gender, okay? And then comma, let's go down to another line. The third argument is let's do ylab equals, which if you guessed it means the y-axis label. And I'm going to create this label or this title for the y-axis, which is selection ratio. And in parentheses, I'm just going to note pass rate in case that's what people are familiar with here. And that is technically what we're looking at. We're talking about pass versus fail, okay? All right, so add a comma after that, but before the parenthesis for the bar plot function. Now, actually, let's just run this as is so you can see this incrementally. So if we run this bar plot function, now you'll see that now our plot has been updated over here with gender and selection ratio as the X and Y titles, axis titles respectively, okay? And if you wanted to save this now, you could save it as an image, copy it to your clipboard, copy it into another document or something like that. We're gonna keep going here though. We're not done yet. So let's add a comma after the xlab equals argument there. So now we are onto our fourth argument. And let's make an adjustment to the y-axis limits here. So you notice that the tallest bar here actually exceeds the limits of the y-axis. And also, if you think about what the lowest possible and the highest possible selection ratio would be, the lowest possible selection ratio would be 0. 0 people passed out of those people who took it. The highest possible would be 1.0, which would mean 100% of people who passed or who took the test actually passed it. Okay, just for the sake of demonstration here, let's extend the y-axis limits to those max and min levels there. So what we're going to do is use the y-lim for y-axis limits. It's just y-lim equals. And then we are going to use the C function from base R, where you can think of C standing for combine. And this is how we can create a vector. Okay, so we're going to vectorize, if you will, the lower and upper limits here for our y-axis. So I'm going to do 0.0, which is our lower limit here, followed by 1.0. You don't need to put a space there. I'll just take out the space there, but this is setting our lower and our upper limits here. You could change this to whatever you want. And in fact, you might change it to whatever you want in terms of what story you're trying to tell here. Now, in this context, we know that if you were to run chi-square test of independence, the 4/5 rule, Fisher exact test, z-impact ratio, z-difference test, pretty much all the conventional adverse impact or disparate impact tests that you might use that are advised by the EEOC and the Uniform Guidelines, you would find that there really isn't evidence of adverse or disparate impact here. So this might be a reason for actually extending the Y limits here, so that you don't want people to walk away. Whereas here they might say, well, that actually looks like that's a substantive, significant difference there between the selection rates for men versus women. But we know that in the actual analyses and the tests that we don't find significant differences. Okay, and so actually, let me just run this chunk now, this function with that additional argument. And so you can see what I mean here. So this minimizes that discrepancy there. Okay. And if you click zoom here, you can get kind of a zoomed out look of the whole thing. All right, so what should we do next? Well, the last thing I'd like to leave you with, and there's a bunch of other ways that we can customize bar plots and so forth. And if you really want to get into that, I would recommend then the next step would be jumping into ggplot2 package with its functions, because that leads to some really high quality potential, publication potential, types of images and figures and plots and graphs and displays that you can create. But let's just explore a little bit with color here. And so let's do COL equals for color equals. And I'll show you something really quick, that if we were to just type in here red, and if you Google R colors, color options, it'll probably give you a few options of websites that have all the different color names that are stock with base R. And that you can access. And so I'll show you a couple here today, but there's a bunch of them that you could use, and you could play around with that if you wanted. But if I just run this as is here, it will make both bars red. Well, let's assume that I want to actually create a visual discrepancy or visual difference between the bar for men and the bar for women here that represent the selection ratios. So it's easier to distinguish that we're talking about two separate protected groups here, or two separate groups, categories within a protected class of gender. Okay. Well, to do that, we'll use our C function again from base R, which is the combine function. And then we would simply say, let's say we want the first bar to be red. Okay, well, we do C, and in our vector, then in parentheses, put red. And then, or rather in quotation marks, put red. And then, comma, our second bar, which would be the second value here in our vector, let's do dark blue. Okay. Because that's one of the stock colors here in R as well. And make sure that, I think I lost the last parentheses that corresponds to the bar plot function itself and not just to the C function. All right, so watch what happens now if we run this. Okay, so now you see that woman has been changed from red to dark blue there. And I think another one of the options off the top of my head is Dodger blue. So watch what happens if we run it like this. Okay, it's a little bit lighter blue there. And so you can get an idea here how you can start customizing the plot. But take a step back and think about what is the story you're trying to tell, and also always take into consideration how the audience is going to interact with this. Is it going to be in a lengthy report where these figures containing these plots might jump out to them, and that might be the only thing people look at? They don't look at the accompanying text that explains. Well, in that case, you might consider, if you think that people might walk away with this still thinking this is a significant difference in selection ratios here. In other words, that if let's say you're using the 4/5 rule, that the impact ratio would be less than 0.80 or less than 4/5, and therefore providing some evidence potentially of adverse or disparate impact, then you might actually decide not to create a data visualization, okay, such as this bar chart here. Again, if you want to export this, you could save the image here, copy it to a clipboard. You could save it as an image such as a JPEG or a PNG, or you can save it as a PDF if that's what you prefer. All right, well, this wraps up this R tutorial, which focused on how do you visualize evidence, or lack thereof, of disparate impact, sometimes called adverse impact, and how do we do so using bar charts.